Welcome everyone to our exploration of computing science, from its fundamental concepts to the latest emerging trends. We'll be taking an in-depth journey through the history and evolution of this dynamic field, covering everything from theoretical foundations to real-world applications. The visual you see on the screen is a digital abstract representation of the world of computing science, with binary code, circuits, and algorithms flowing through a modern technological landscape. The dramatic lighting and vibrant blue and purple colors help to convey the power, complexity, and innovation that characterize this field. Over the course of this presentation, we'll dive into the key principles, breakthroughs, and future directions that are shaping the future of computing science. Computing science is the systematic study of algorithmic processes that create, describe, and transform information. The core objectives are developing efficient algorithms, creating usable software, and building computational systems. Computing powers everything from smartphones to supercomputers, transforming industries worldwide. Computing has become essential in our daily lives and is a critical field that enables technological advancements across many sectors. The image on this slide sets the stage for our journey through the history of computing, featuring vintage devices like mechanical calculators, early mainframes, and vacuum tubes. We'll start in 1837 with Charles Babbage's design of the analytical engine, considered the first mechanical general-purpose computer. In 1936, Alan Turing published his groundbreaking work on computable numbers, introducing the revolutionary Turing machine concept. Then in 1945, we see the emergence of ENIAC, the first programmable, electronic, general-purpose digital computer. These key milestones laid the foundation for the incredible technological advancements we've witnessed in computing over the past century. The Turing machine is a theoretical mathematical model that represents a simple computing device. It has an infinite tape, a read/write head, and a set of state transition rules that define its behavior. This model was established by Alan Turing as the theoretical foundation for the concept of an algorithm. It proved that a single machine could compute anything that is computationally possible, giving it universal significance in computer science. The Turing machine laid the groundwork for our modern understanding of computation and the capabilities of computers. Ada Lovelace is considered the first computer programmer, having written an algorithm for the analytical engine in the 1840s. Grace Hopper was a pioneering computer scientist who developed the first compiler and helped create the COBOL programming language. Donald Knuth is a renowned computer scientist who authored the influential multi-volume work, The Art of Computer Programming, which has had a major impact on the field. These three individuals made groundbreaking contributions that shaped the early development of computing and programming. Computing is built on a few fundamental concepts that are essential to understand. The first is abstraction, simplifying complex systems by focusing on the relevant details and ignoring the unnecessary complexity. Algorithms are another key concept. These are step-by-step procedures for calculations or problem-solving. Finally, computation is the actual process of executing these algorithms to transform data. Binary is a number system that uses only 0 and 1. Decimal is the standard human counting system, using numbers 0 to 9. Hexadecimal uses 0 to 9 and AF to represent 16 different values. Octal is a base 8 number system, using only the digits 0 to 7. The table shows examples of how these different number systems represent the same value. For instance, the binary number 1101 is equivalent to the decimal number 13 and the hexadecimal number D. Understanding how to convert between these number systems is important for working with computers and digital systems. Computers at their core only understand zeros and ones, so being able to translate between binary and other formats is crucial. Logic gates are the fundamental building blocks of digital circuits. They perform basic Boolean logic operations on one or more binary inputs. The four main logic gates are AND, OR, NOT, and XOR. The AND gate outputs a 1 only if all inputs are 1. The OR gate outputs a 1 if at least one input is 1. The NOT gate inverts the input. 0 becomes 1, and 1 becomes 0. The XOR gate outputs a 1 if the inputs are different. Digital circuits can be divided into two main categories: combinational circuits and sequential circuits. Combinational circuits have outputs that depend only on the current inputs, without any memory or previous state. Examples of combinational circuits include logic gates, multiplexers, and decoders. Sequential circuits have outputs that depend on both the current inputs and the previous state or memory. Examples of sequential circuits include flip-flops, registers, and memory elements. The key distinction is that sequential circuits have some form of memory or state that affects the output, while combinational circuits do not. The von Neumann architecture is a fundamental computer design that has been widely used since the 1940s. It consists of four main components: the CPU, memory, input-output, and a bus that connects them. The CPU processes instructions and performs calculations, acting as the brain of the computer. Memory stores the program instructions and data that the CPU needs to access. Input-output components interface with external devices and users, allowing for data to be entered and retrieved. The bus is the communication pathway that transfers data between the different components. This interconnected design allows computers to execute programs and manipulate data in a systematic way. The von Neumann architecture has been highly influential and continues to be the basis for modern computer architectures. The key hardware components that make up a modern computer system. We'll take a closer look at the CPU, RAM, storage drives, and graphics cards. These are the core components that power the computing power and capabilities of a PC. Each of these components plays a critical role in determining the overall performance and functionality of the system. We'll explore the features and specifications of these components in more detail in the upcoming slides. Moore's law is an observation that the number of transistors on a microchip doubles approximately every 2 years, while the cost of computers is halved. This chart shows the exponential growth in the number of transistors on a microchip over the past 50 years, from just 2,000 in 1971 to over 39 million in 2019. The rapid pace of innovation in semiconductor technology has enabled incredible advancements in computing power and affordability. This trend has fueled the digital revolution and enabled the widespread adoption of personal computers, smartphones, and other modern technologies. While the physical limits of silicon-based transistors are being approached, new materials and architectures continue to drive progress, suggesting Moore's law may continue for years to come. Software is divided into 3 main categories: system software, application software, and programming software. System software manages hardware resources and provides services for applications like Windows, Linux, and Mac OS. Application software performs specific tasks for users, such as Microsoft Word, Adobe Photoshop, and web browsers. Programming software includes the tools developers use to create software, like compilers, debuggers, and integrated development environments. These 3 types of software work together to enable the full functionality of computers and other digital devices. Windows is the dominant operating system for personal computers, with around 75% market share. Mac OS powers Apple computers and is known for its seamless integration between hardware and software. A Linux is an open-source operating system that powers most servers and supercomputers globally. The mobile OS market is dominated by Android and iOS, which power smartphones and tablets. Programming languages can be categorized into high-level, mid-level, and low-level based on their level of abstraction from the underlying hardware. High-level languages like Python, JavaScript, and Java are human-readable and highly abstract, making them easier for developers to work with. Mid-level languages like C and C++ strike a balance between abstraction and control, allowing for more direct access to system resources. Low-level languages like assembly provide direct access to hardware instructions, giving programmers fine-grained control but requiring more technical expertise. The choice of programming language depends on the specific requirements of a project, such as performance needs, development time, and the level of control required. This slide introduces the classic Hello World program in multiple programming languages. We'll look at the syntax for printing the simple message in Python, Java, C, JavaScript, and Ruby. The goal is to show how the basic structure of this program is similar across different languages, despite the specific syntax differences. Highlight how the core logic is the same: print a string to the console or output. Note the slight variations in syntax, like using print versus system.out.println, versus printf versus console.log versus puts. Emphasize that this is a fundamental starting point for learning any new programming language. Explain that hello world demonstrates the most basic program structure and helps new programmers get familiar with a language's syntax. The core foundations of algorithms are problem analysis, algorithm design, implementation, and testing and refinement. Problem analysis involves clearly defining the problem and identifying the required inputs and expected outputs. Algorithm design is the process of creating a step-by-step procedure to efficiently solve the problem. Implementation converts the algorithm into code using a programming language. Testing and refinement verifies the correctness of the implementation and optimizes it for performance. These 4 stages form the fundamental life cycle of developing effective algorithms to solve complex problems. Algorithm complexity is a way to analyze and compare the efficiency of different algorithms. The chart shows how the runtime of different algorithms scales with the size of the input. Constant time, O1. Algorithms have a runtime that doesn't depend on the input size. Logarithmic time, O log n. Algorithms have a runtime that grows slowly as the input size increases. Linear time, O n. Algorithms have a runtime that grows proportionally with the input size. Quadratic time, O n superscript 2. Algorithms have a runtime that grows quickly as the input size increases. Understanding algorithm complexity helps us choose the most efficient algorithms for our needs. Sorting algorithms are fundamental to computer science and are used to arrange data in a specific order. I'll briefly cover 4 popular sorting algorithms: bubble sort, merge sort, quick sort, and heap sort. Bubble sort is a simple algorithm, but it's inefficient with a time complexity of O and superscript 2. It works by repeatedly swapping adjacent elements if they're in the wrong order. Merge sort is a divide-and-conquer algorithm with a time complexity of O and log n. It's a stable and predictable algorithm that works by splitting the array, sorting the halves, and then merging them back together. Quicksort is also O and log n on average, and it's very fast in practice. It uses a pivot element to partition the array, then recursively sorts the 2 partitions. Heap sort has a time complexity of O and log n, and uses a binary heap data structure to efficiently sort the elements. Data structures are fundamental building blocks for organizing and storing data in computer programs. They provide efficient ways to access, manage, and manipulate information. This presentation will cover 4 essential data structure concepts: arrays, linked lists, binary trees, and graphs. Each of these data structures has unique characteristics and use cases that make them suitable for different programming tasks. We'll explore the visual representations, key properties, and common applications of these data structures. Arrays and linked lists are 2 fundamental data structures in computer science. Arrays store elements in contiguous memory, allowing for constant-time random access. However, arrays often have a fixed size, limiting their flexibility. Linked lists, on the other hand, store elements in non-contiguous memory and have a dynamic size that can grow efficiently. Accessing elements in a linked list takes linear time, but linked lists are more efficient for frequent insertions. The choice between arrays and linked lists depends on the specific requirements of the application, such as the frequency of reads versus writes, and the need for random access or dynamic resizing. Stacks and queues are 2 fundamental data structures in computer science. Stacks follow a last-in, first-out, LIFO, principle. The last item added is the first one removed. Key stack operations are push, add to top, and pop, remove from top. Stacks have many applications, like function calls and undo features in software. Queues follow a first-in, first-out, FIFO, principle. The first item added is the first one removed. Key queue operations are enqueue, add to rear, and dequeue, remove from front. Queues have applications in processing tasks like print jobs and message processing. The visual examples help illustrate the LIFO and FIFO principles clearly. Trees are a fundamental data structure in computer science with many important applications. Binary search trees are a specific type of tree that allow for efficient searching, insertion, and deletion of values. The key properties of binary search trees are: search, find a value by comparing against nodes with an average time complexity of O log n. Insert, Add new values while maintaining the tree's order, also with an average time of O log n. Delete. Remove values while preserving the tree structure, again with an average time of O log n. Traversal is also an important operation, allowing you to visit all nodes in a specific order, in order, pre-order, post-order. These properties make binary search trees very useful for a variety of applications, from databases to file systems. Graphs are a powerful data structure for modeling relationships and connections between entities. There are different types of graphs: directed versus undirected, weighted versus unweighted, cyclic versus acyclic. Graphs can be represented in different ways: adjacency matrix, adjacency list, edge list. Graphs have many real-world applications, like modeling social networks, route finding, and dependency resolution. The key is understanding the different graph types and representations, and how to choose the right one for your specific use case. Hash functions are used to convert input data into a fixed size value, which serves as an index. Hash tables are a data structure that implement key value storage with fast lookup times. Collision handling techniques like chaining or open addressing are used to resolve index conflicts when multiple keys hash to the same index. Hash tables provide O(1) average time for insert, delete, and lookup operations, making them highly efficient. Recursion and iteration are two fundamental programming concepts. Recursion is when a function calls itself to solve smaller instances of the same problem. The example shows a recursive function to calculate the factorial of a number. Iteration is when a loop is used to repeat a process until a condition is met. The example shows an iterative function to calculate the factorial of a number. Both recursion and iteration can be used to solve the same types of problems, but they have different approaches and trade-offs. Recursion can sometimes be more elegant and concise, but it can also be more memory-intensive. Iteration is often more efficient and easier to understand, but it can require more code. The choice between recursion and iteration depends on the specific problem and the constraints of the system. The software development lifecycle is a structured process that teams follow to build and maintain software. It consists of 5 key phases: requirements, design, implementation, testing, and maintenance. In the requirements phase, we gather and document the software specifications and user needs. The design phase involves creating technical specifications for the software architecture and interfaces. During implementation, the code is written according to the design specifications. Testing verifies that the software meets the requirements and any defects are fixed. Finally, the maintenance phase involves updating and improving the software throughout its lifecycle. Object-oriented programming is a programming paradigm that focuses on creating objects, self-contained units of data and code. These objects have 4 key principles: encapsulation, bundling data, and methods that operate on that data into a single unit; inheritance, creating new classes based on existing ones, inheriting their attributes and behaviors; polymorphism, objects of different classes responding to the same interface in different ways; abstraction, hiding complex implementation details while exposing only necessary functionality. This slide provides a high-level overview of these 4 core OOP concepts. I'll dive deeper into each one to help the audience understand how they work in practice. Functional programming is a programming paradigm that emphasizes the use of pure functions, immutable data, and higher-order functions. Pure functions are functions that have no side effects and always return the same output for the same input. Immutability means that data cannot be changed after it's created. Instead, modified copies are created. Higher-order functions are functions that can take other functions as arguments or return them as results. Recursion is a technique where functions call themselves to solve problems, replacing iteration as the primary control structure. These principles help create more modular, testable, and maintainable code. Parallel computing involves multiple processors executing computations simultaneously, enabling faster processing of complex tasks. This is achieved through hardware parallelism, a divide-and-conquer approach, and is commonly used in supercomputing applications. Concurrent computing, on the other hand, involves multiple computations executing during overlapping time periods, often through thread-based multitasking and shared resource management, as seen in web server applications. The key difference is that parallel computing focuses on simultaneous execution, while concurrent computing focuses on overlapping execution over time. Both parallel and concurrent computing techniques are essential for optimizing performance and efficiency in a wide range of applications, from scientific simulations to web-based services. Cloud computing is a model for delivering IT services over the Internet. There are three main types of cloud computing services: software as a service, SaaS, ready-to-use applications delivered via the web; platform as a service, PaaS, development and deployment environment in the cloud; infrastructure as a service, IaaS, virtual computing resources over the Internet. These cloud services allow organizations to access technology capabilities without having to build and maintain the underlying infrastructure themselves. This can provide benefits like scalability, flexibility, and cost savings compared to traditional on-premises IT. Distributed systems are made up of multiple independent computers that communicate over a network. These systems coordinate actions and tasks despite the physical separation of the nodes. They are designed to be scalable, allowing the capacity to grow by adding more nodes to the system. Distributed systems are also built to be fault-tolerant, continuing to function even when individual components fail. This allows for highly reliable and available systems that can handle large workloads and withstand failures. The networking stack is made up of several key layers, each with a specific function. The physical layer deals with the hardware transmission of raw data bits. The data link layer handles node-to-node data transfer and error correction. The network layer is responsible for routing packets across different networks. The transport layer provides end-to-end connection and reliability. The application layer contains high-level protocols for specific applications. Each layer plays an important role in enabling network communication and data transfer. The Internet is a vast network of interconnected devices, routers, and servers that enable the exchange of information around the world. When a user makes a request from their device, the domain name is first converted to an IP address through the domain name system (DNS). The data packets then travel across multiple networks, being routed through various nodes before reaching the appropriate server. The server processes the request and sends the requested data back to the user's device, completing the cycle. This process happens seamlessly, allowing users to access information, communicate, and interact with online services with ease. Cybersecurity is built on key principles that help protect information and systems. Confidentiality is about ensuring sensitive data is only accessed by authorized individuals. Integrity means maintaining the accuracy and completeness of information so it can be trusted. Availability ensures users and systems have reliable access to the resources they need. Authentication verifies the identity of people and devices before granting access. Authorization determines what level of access and permissions different users should have. These core principles form the foundation of effective cybersecurity practices. Cryptography is a fundamental aspect of computing, enabling secure communication and data protection. There are three main types of cryptographic techniques used in computing: symmetric encryption, where the same key is used for both encryption and decryption. Examples are AES and other fast symmetric ciphers. Requires a secure way to exchange the shared key. Asymmetric encryption, using public and private key pairs. RSA is a widely used asymmetric algorithm. Solves the key distribution problem, but is slower than symmetric encryption. Hashing, which creates fixed size values from data through one-way functions. Examples are SHA, 256, and MD5. Used to verify data integrity without revealing the original data. Relational databases are a well-established technology for managing structured data, organized in tables with predefined relationships. Some popular examples include MySQL, PostgreSQL, and Oracle. These databases adhere to the ACID, atomicity, consistency, isolation, durability principles, ensuring data integrity. Structured Query Language, SQL, is the standard language used to interact with relational databases. In contrast, NoSQL databases offer a more flexible approach to handling unstructured data with the ability to scale horizontally. Examples of NoSQL databases include MongoDB, Cassandra, and Redis. NoSQL databases typically prioritize high throughput and a distributed architecture, often sacrificing some of the strict guarantees provided by relational databases. This makes them well-suited for handling large, rapidly changing datasets that don't fit neatly into the tabular structure of relational databases. SQL is the standard language for interacting with relational databases. It provides a set of powerful commands for querying, manipulating, and managing data. The key SQL commands shown here are select, insert, update, delete, and join. Select retrieves data from a table based on specified criteria. Insert adds new records to a table. Update modifies existing records in a table. Delete removes records from a table. Join combines data from multiple tables based on a related column. These examples demonstrate the basic syntax and usage of these SQL commands. Mastering SQL is an essential skill for anyone working with databases and data. Web development is built on three core technologies: HTML, CSS, and JavaScript. HTML provides the structure and content of web pages, using tags to define elements like headings, paragraphs, images, and more. CSS controls the presentation and layout of those web elements, allowing you to style the appearance of a page. JavaScript adds interactivity and dynamic behavior to websites, enabling features like drop-down menus, form validations, and animations. These three technologies work together to create the rich, interactive web experiences we see today. Mobile computing is a key part of today's technology landscape, with two major platforms dominating the market: Android and iOS. Android is an open-source platform developed by Google, allowing for a diverse device ecosystem. It utilizes Java and Kotlin programming languages and has around 70% global market share. In contrast, iOS is Apple's proprietary platform, known for its consistent hardware integration. It uses Swift and Objective-C programming languages and has around 30% global market share. Both platforms offer robust development environments and ecosystems for building mobile applications. The choice between Android and iOS often depends on factors such as target audience, development resources, and desired user experience. Embedded systems are specialized computer systems designed to perform specific tasks, often found in devices like appliances, vehicles, and medical equipment. They are characterized by their small size, low power consumption, and real-time processing capabilities. Embedded systems can be found in a wide range of applications, from smart home devices to industrial automation and medical equipment. The images on this slide showcase some examples of embedded systems, including microcontroller boards, smart thermostats, pacemakers, and home security systems. These systems are designed to be reliable, efficient, and often operate in environments where traditional computers would not be suitable. Graphics and visualization are core capabilities that power many modern technologies. 3D rendering is the process of converting 3D models into 2D images using techniques like rasterization and ray tracing. Data visualization helps reveal patterns and insights by representing data graphically. Real-time graphics generate images fast enough for interactive applications like video games. VR and AR rendering creates immersive visual experiences for virtual and augmented reality. Artificial intelligence is a broad field that encompasses different approaches and capabilities. General AI refers to the hypothetical goal of creating AI with human-like intelligence across many domains. Machine learning is a key technique in AI, where systems learn from data without explicit programming. Expert systems are rule-based AI systems designed for specific domains of knowledge. Machine learning is a powerful tool for extracting insights from data. The key steps in the machine learning process are: data collection, gathering and preparing relevant datasets; model training, algorithms learn patterns from the training data; evaluation, testing performance on new data to assess accuracy; refinement, tuning parameters to improve the model's predictive power; deployment, implementing the model in real-world applications. Each of these steps is critical to developing an effective machine learning solution. I'll go into more detail on each of these steps in the upcoming slides. Deep learning is a powerful machine learning technique that uses artificial neural networks to learn from data. Neural networks are inspired by the structure and function of the human brain, with interconnected nodes, neurons, that transmit signals between each other. The basic structure of a neural network has three key components. Input layer receives the raw data that will be processed by the network. Hidden layers extract increasingly complex features and patterns from the input data. Output layer produces the final predictions or classifications. As the data flows through the network, the hidden layers learn to recognize more and more sophisticated characteristics, allowing the model to make accurate forecasts or decisions. Natural language processing is a field of artificial intelligence that focuses on the interaction between computers and human language. It encompasses a range of capabilities, including text classification, machine translation, named entity recognition, and text generation. Text classification involves categorizing documents or messages by topic, sentiment, or intent. This can be useful for things like spam filtering or customer service automation. Machine translation converts text from one language to another while preserving the original meaning. This enables communication across language barriers. Named entity recognition identifies important elements in text like people, organizations, locations, and other entities. This can aid in information extraction and knowledge representation. Text generation creates new coherent and contextually appropriate text from prompts. This can be used for tasks like summarization, dialogue, and creative writing. These NLP capabilities have a wide range of applications in areas like customer service, content analysis, language learning, and more. The rise of robotics and automation has transformed the manufacturing industry, with a 60% increase in industrial robot deployment since 2016. Robotic systems can operate 24/7 without human fatigue, providing continuous productivity for manufacturing operations. Household robotics have also seen significant growth, with over 113 million consumer robots in use globally. Robotics and automation are driving increased efficiency, productivity, and cost savings across a wide range of industries. As the technology continues to advance, we can expect to see even more widespread adoption of robotic systems in the years to come. Quantum computing is a new paradigm that leverages the principles of quantum mechanics to perform computations. At the heart of quantum computing are qubits, which can exist in a superposition of states, unlike classical bits that are limited to 0 or 1. This superposition allows qubits to represent multiple states simultaneously, enabling quantum computers to perform certain computations much faster than classical computers. Quantum entanglement is another key principle where particles can become correlated in a way that their states are linked, even over large distances. Quantum gates are the operations that manipulate qubits to perform computations on a quantum computer, similar to how logic gates work in classical computers. Quantum algorithms like Shor's and Grover's offer significant speedups over classical methods for certain problems. Shor's algorithm can efficiently factor large numbers, which threatens the security of current cryptographic systems like RSA. It provides an exponential speedup over classical factoring algorithms, but requires large-scale, fault-tolerant quantum computers to be practical. Grover's algorithm offers a quadratic speedup for search problems and is more feasible to implement on near-term quantum hardware. Both of these algorithms demonstrate the power of quantum computing and its potential to disrupt various fields, from cryptography to optimization. The increasing use of automation and AI in the workplace is leading to the displacement of many routine jobs, but it's also creating new roles that require different skills. As we collect more and more data about individuals through digital technologies, there are growing concerns about privacy, data collection, and surveillance capabilities. The use of algorithms in decision-making raises important ethical considerations around bias, transparency, and accountability. Unequal access to technology around the world is creating a digital divide, leading to socioeconomic disparities between those who can access and utilize computing technologies and those who cannot. The data on this slide highlights the significant diversity gap in the computing field compared to the general population. Women make up just 23% of the computing workforce, despite being 51% of the general population. Black and Hispanic individuals are also underrepresented, making up only 8% and 9% of the computing workforce respectively, compared to 13% and 19% of the general population. In contrast, Asian individuals are overrepresented, making up 25% of the computing workforce compared to 6% of the general population. The data underscores the need to improve diversity and inclusion efforts in order to better reflect the diversity of our society within the computing field. Data centers worldwide use 1.5% of global electricity, so improving their efficiency can have a significant impact. Efficient computing practices have the potential to reduce energy consumption by up to 60%. However, the growing problem of e-waste is also concerning, with 30 million tons of electronic waste generated annually. Addressing both energy efficiency and e-waste is crucial for making computing more sustainable. The image on this slide depicts an eco-friendly data center with features like solar panels, natural cooling systems, and other green technologies. This represents the kind of sustainable architecture and infrastructure we need to pursue. Transitioning to greener, more efficient computing will be vital for reducing the environmental impact of the technology sector. The image on this slide depicts a smart city infrastructure with IoT sensors and edge computing devices processing data locally. The slide outlines the key steps in the edge computing and IoT process. Data collection. IoT devices gather real-time data from the environment. Local processing. Edge devices analyze data near the source. Data filtering. Only relevant information is transmitted to the cloud. Cloud integration. Aggregated data enables broader insights and management. This approach allows for faster, more efficient data processing and reduced bandwidth requirements compared to a centralized cloud-based model. The combination of edge computing and IoT enables smart city applications that can respond to local conditions in real time. High-performance computing, or HPC, refers to the use of powerful, specialized computers and computing systems to tackle complex, data-intensive problems. These supercomputers are designed to perform trillions of calculations per second, enabling the modeling and simulation of complex scientific and engineering phenomena. HPC systems often feature specialized hardware like parallel processors, large amounts of memory, and advanced cooling systems to handle the immense computational loads. The visualizations and simulations generated by HPC can provide deep insights into fields like fluid dynamics, climate modeling, molecular biology, and more. HPC enables researchers and scientists to push the boundaries of what's possible, accelerating discovery and innovation across a wide range of disciplines. Privacy regulations like GDPR in Europe and CCPA in California are establishing new data privacy rights for individuals. These include the right to be forgotten, data portability, and requirements for clear consent. Ethical frameworks are being developed to ensure AI systems are fair, transparent, and have appropriate human oversight. The evolution of copyright and patent law is grappling with how to protect intellectual property for digital assets like software and open source code. Issues around software patents, open source licensing, and digital rights management are being actively debated. Blockchain is a distributed ledger technology that ensures transparent and immutable record-keeping. Cryptocurrencies are digital assets that use cryptography for secure financial transactions. Smart contracts are self-executing agreements with terms directly written in code. NFTs, or non-fungible tokens, represent unique digital assets and ownership. The AR/VR industry is projected to be a $31 billion market by 2024, indicating significant growth potential. 71% of large enterprises are already implementing AR/VR technology, showcasing the widespread adoption of these technologies in the business world. There are currently 78 million active users of AR/VR applications globally, demonstrating the increasing popularity and reach of these immersive technologies. The image on the slide depicts a person using a VR headset, interacting with virtual objects in a real-world environment, highlighting the capabilities of augmented and virtual reality. These statistics and the visual representation aim to convey the scale, adoption, and impact of AR/VR technologies, setting the stage for the rest of the presentation. The future of computing holds exciting advancements on the horizon. By 2025, AI assistants will become ubiquitous across industries and personal computing, transforming how we interact with technology. By 2030, edge AI processing power will exceed current cloud capabilities, enabling more intelligent and responsive devices. Neural interfaces will reach the consumer market by 2035, allowing for direct brain-computer interaction. By 2040, quantum computing will become mainstream for specific commercial applications, unlocking new possibilities in fields like cryptography and materials science. Computing careers are experiencing rapid growth, with some fields like AI/machine learning seeing over 35% projected growth. Software development, cybersecurity, and data science are also seeing very strong demand, with 22 to 32% projected growth. Cloud computing, while not growing as quickly as some other areas, is still expected to see 15% growth in the coming years. These are all exciting and in-demand fields that offer great opportunities for those interested in computing and technology careers. The strong growth across these areas shows the continued importance and expansion of the tech industry. Individuals with the right skills and training can find rewarding and future-proof careers in these dynamic computing fields. Computing science has a rich history, evolving from theoretical concepts to transformative technologies that shape our world today. The foundational principles of algorithms, data structures, and architecture remain essential, even as the field continues to advance. Computing science has an interdisciplinary impact, transforming every industry from healthcare to finance with new capabilities and innovations. The future holds exciting horizons, with emerging fields like quantum computing, AI, and new interfaces redefining what's technologically possible.